Okay, so hello everyone and welcome again for the live session, live session number 7 for the course Introduction to Semiconductor Devices. As you know, it is being taught by Professor N.K. Emani of IIT Hyderabad, and I am Samadhan Kamble, your PMRF TA for conducting these live sessions. So we are almost or more than halfway through this NPTEL course. We are now in the seventh week of the course. End of the 7th week indeed. So we are more than halfway through what we wanted to cover. But let me tell you that this is the beginning of the actual fun part. So far in the first half of the course, what we have done is laid down the basics, the foundations of this course, and now here on till the end of the course we will be building on this foundation the devices that are supposed to be taught. So these devices, the basics and fundamentals have been taught so far, and we'll go into the actual devices from now on. So I think this is actually a very important phase that is going to begin from the 7th week. Okay, so as you know, the format for these live sessions from my side is that in the first 10 to 15 minutes, I'll give a brief description of what has been covered in the current week lecture contents. That will be a quick refresher for you going ahead in solving the assignment problems that we will do. And again, after this short recap, we will go to the actual problem solving, which are from the previous course, also from the previous competitive exams related to this week, of course. And as I have been telling you that you can stop me at any time if you have any difficulty. Okay, so in the previous week, like the week before this Monday, we were discussing the operation of Mos capacitors, and we argued that the Mos capacitors are basically at the heart of the Mos devices. For example, the MOSFETs, which is Mos field effect transistors. So we then looked at the depletion, inversion, and accumulation regimes of the mass capacitors, and we also understood them based on the simplified band diagrams. However, we just looked at the semiconductor part of it, semiconductor part of the MOS capacitors. So in this week, our aim probably most of the time was to go deeper into the understanding of the electrostatics of the MOS capacitors and not only the semiconductor part of it. So as I said, studying the characteristics of energy bands as a function of the applied voltage in the MOS capacitors was the primary aim. So far we were only concerned about the energy band diagrams of the semiconductor material. So in the previous live session I showed the energy band levels of the MOS capacitors and the silicon dioxide, which is the oxide material which acts as the insulator in the MOS capacitors. We showed different parameters such as the work function of the metal, that is phi m, the electronic affinity chi, and different parameters such as chi I and so on. So let us go to the slide number 1 first. Okay, so the Mos Electrostatics is what was a primary aim. So as you can see in the figure that is accompanying here, so this figure shows the energy band diagram of the entire MOS structure. So entire MOS metal oxide semiconductor structure with zero gate voltage applied. So the Fermi level, as you can see, is a constant through the entire system as at the thermal equilibrium, and we may define a parameter called as phi m prime, which is nothing but the modified metal work function, which is the potential required to inject an electron from the metal into the conduction band of the oxide. Similarly, chi prime is also the modified electron affinity. The voltage V oxide 0 is the potential drop across the oxide for 0 applied gate voltage, but you would argue that when we don't apply voltage, then how there can be a potential drop. but the voltage Vox 0 is not necessarily 0 because of the difference between the phi m and chi. Also, the potential phi s naught is shown here, which is the surface potential for this case. So in a MOS capacitor, a lot could be understood from the band bending in the semiconductor. So we have been emphasizing about the band bending and the band diagrams. So if you consider phi s, which is the potential at the surface, and phi is equal to 0 is the potential inside the bulk, then minus q phi s is the total band bending in the semiconductor, and the negative phi s means the band is bending upwards, and the positive phi s means the band is bending downwards. So as you can see, the phi s is given by this particular relation. Phi s is the energy level at the bulk minus the energy level EI, intrinsic level, at the surface. Okay. Also you can see that an important material parameter related to the semiconductor doping is called as the phi f, and it is given as EI bulk minus EF. So phi f, as you can see here, just a moment. Okay, so phi f, as you can see here, is the difference between the intrinsic band at the bulk minus the Fermi level. So as we know that this particular parameter is function of the doping concentration, and also the sign of phi f indicates the doping type. So for example, if phi f is more than 0, that means the phi f is more than 0, that means the Fermi level is downwards than the intrinsic level, which corresponds to p-type semiconductor, p-type which is in which the Fermi level is close to the valence level. So this is for the p-type. And when the phi f is negative, that means the Fermi level is above the intrinsic level, and that will correspond to the n-type. Just a moment. Okay, so that will correspond to the n-type semiconductor. So this parameter, as I told you, is important, and which is function of the doping concentrations. So this is acceptor, so it is p-type semiconductor. This is donors, n-type semiconductor, and as I explained, phi f is negative for n-type and it is positive for the p-type semiconductors. Also, the parameters phi s and phi f are extensively useful in specifying the biasing state inside the semiconductor. So clearly at flat band condition, phi s is going to be 0 because there won't be any band bending. Moreover, phi s is equal to twice phi f is at the depletion inversion transition point. So we saw that this is a threshold potential, and with phi f increasing inside the p-type semiconductor, it follows that the biasing conditions are as follows. If phi s is less than 0, that means we are in the accumulation region. If the phi s is in between 0 and phi f, we are in the depletion, and when phi s increases more than phi f, it is the inversion region. For an n-type semiconductor, the inequalities are just reversed of what has been shown here. Also, we can define an important potential here. It is called as phi ms, which is nothing but the difference of phi ms is nothing but difference of work function of the metal and the semiconductor, and this is also written here, which is the function of different parameters like the chi prime, phi m, phi fe, and the band gap Eg. 1 minute. Okay, so let us go to the slide number 2. I think the Mos electrostatics has been explained in the slide number 1. Going to the slide number 2, the different important formulae I have just summarized here related to the Mos electrostatics. So In the standard depletion approximation, the actual depletion charge is replaced with a square of distribution terminated abruptly at a distance of x, which is equal to W, that is total width, into the semiconductor. So let us assume a p-type semiconductor and also invoke the depletion approximation. We have the following important formulae. As you can see here, I have just summarized them all here, and it will be useful for the problem solving. The electric field, the electrostatic potential, the surface potential at x is equal to 0, depletion width, and also the maximum depletion width. So all these parameters I have summarized, which are function of the applied doping, and also the epsilon for the silicon, and yeah, I think so. These are summarized here. So let us go to the slide number 3, which is the final slide for the summary here. Okay, so it is about the gate voltage relationships. So the external applied gate voltage is the ideal in the ideal structure is dropped partly across the oxide and partly across the semiconductor. So as you can see in this figure, when we applied the gate potential, it gets dropped. The potential drop happens at the oxide side first and then at the semiconductor side. So addition of those two potential drops is nothing but the applied gate voltage. So it is written by delta phi oxide, that is voltage drop at the oxide region, and phi s at the semiconductor side. So this is delta phi oxide is substituted by this particular relation, and if you just compare or just take into account equation number 3 and 6, we'll get the electric field in the silicon side as given by this particular relation. And so if we substitute this value in the equation number 8, we get the gate voltage relationship with respect to phi s by equation number 10. So this is an important equation to remember. So I think this constitutes a good summary of this week's contents, and I think we are ready to go to the questions, the assignment problems. So let us go to the first question, and the question number 1 is as follows. So the objective of the question is the following. So what we have asked is to determine the metal semiconductor work function difference, that is phi ms, for a given MOS system and semiconductor doping. So the example is of an aluminum silicon dioxide junction in which phi m prime is given by 3.20 volt, and for a silicon dioxide junction, chi prime, that is the modified electron affinity, is given by 3.25 volt. Also we can assume the band gap as 1.12 volt, and the p-type doping is also given. So we need to find out the work function difference, that is phi ms. So going to the recap slide, we saw that the phi ms can be given by this particular equation, and in which different parameters are given, like phi m prime is also given, eg, and chi prime is also given. However, phi fv is not given, and we need to think that how can we get the value of phi fp. So from the diagram you can see that phi fp is the region here which is a difference of the intrinsic level and the Fermi level, and it is as a function of the applied doping concentration. So we know that phi fp is given by Vt ln of Na by Ni. So Na is the doping here and Ni is the intrinsic concentration. So if for 300 Kelvin, if we can consider, we can just substitute Vt as 0.0259 or 226, then ln of Na in our case is 10 to the power 15 per centimeter cube divided by the intrinsic charge carrier concentration, and we can take that as 1.5 times 10 to the power 10. So if you just calculate this, we will get value of phi fp as 0.288 volts. Okay, so now we have all the parameters required to determine the phi ms, which is given by phi ms is nothing but phi m prime minus chi prime plus Eg over twice E plus phi fp. So just a mere substitution here, phi m prime, which is nothing but 3.20 minus chi prime is 3.25 plus Eg is Eg by twice E, we can directly substitute as 0.560 plus the phi fp that we determined, that is 0.288. So if you just do the summation and subtract in here, we'll get the work function difference phi ms as minus 0.898 volt. Okay, so one thing to note here is that the value of phi ms is dependent on value of phi fp, which is further dependent upon the doping concentration Na. So the value of phi ms will be more negative as the doping of the p-type substrate increases. If the doping increases, then this value increases. If this value increases, this quantity decreases and it becomes more negative. So that is one important thing to note here. Okay, so I think let us go to question number 2, which is in fact for the common data. It is common data for question number 2 to 10. I think there are 9 small questions, 1 mark each, based on the data given in this particular slide. So I'll just read out the data for you. The energy band diagram of a MOS capacitor device is sketched here in the figure 1 below, and we need to assume the electrostatic potential is 0 in the semiconductor bulk. That is, we are considering the large distance from the silicon and silicon dioxide interface, and also that there is no metal semiconductor work function difference. So phi ms, that is phi m minus phi s, is 0, and also assume the relative dielectric constants of the oxide to be 3.9. Different parameters are also shown here. Okay, so based on this data and based on this particular energy band diagram, we need to answer following questions. So let us directly go to the questions. So the first question is the following: what is the value of phi f or phi fp? So I think these are very simple questions. I expect answers from you guys. So please pitch in and just tell me. So the first question is the value of phi f is asked. So looking at the diagram, can you tell me what is the value of phi f? We also saw the uh, definition of phi f. Can you just tell me? Just attempt. Anyone? Okay. If not, okay, so I'll tell then. As we I have written in this summary slide itself that the phi f is nothing but the intrinsic level at bulk minus the Fermi level. So here you can clearly see that the intrinsic level at the bulk and the phi f difference is shown directly here as 0.437. But remember, we have to get the difference as phi f is EI in the bulk minus EF, and in our case the EF is on the upside of the intrinsic level, that is we are in the N side. For that the phi f value is negative, so we have negative 0.437 volt as our answer for phi f. Okay, let us move to question number 3 then. These are like quite small questions based
Sir,
on
sir, hello, sir. Can you explain why it was negative?
Okay, I'll explain it again. Okay, so as you can see here, in the diagram itself, this axis is the energy axis. Okay, now the value of phi f is ei minus ef. So in this itself we can see that ei in the downside and ef is on the higher side, so ef is more than ei. So if you just apply the algebra, this quantity would dominate and which has the negative sign. That means this difference is negative. We saw here also that the phi f is negative for n type because the Fermi level is above the intrinsic level. We are calculating difference between intrinsic level and the Fermi level. If the Fermi level is below the intrinsic level, that means Fermi level is at higher energy, and that will give us the positive value of phi f. Whereas for the n type, it is the other way around. ef is on the higher energy side, and that means it will give us the negative value. Is it clear?
Yes, sir.
Okay. So let us go to question number 3 again. As I told you, these are like very simple but intuitive questions. What is the surface potential phi s? Again, just going to the summary slide. If you just recall the equation number 1, phi s is given as ei on the bulk minus ei on the surface. Okay, ei bulk minus ei surface. If you just go to the diagram and let's see what is the value. ei on the bulk and ei on the surface. So this bending or this bending or this bending, all three are same. So this bending we need to determine, and that is nothing but the phi s. So it is itself given here. You can see that it is 0.24 electron volt, and also we saw that when the bands bend upwards, the phi s is negative because the surface on the surface side, the ei surface is more than ei bulk. That means the negative part is dominating, giving us the phi s value as negative. So in our case also, we can say that the band is bending upwards, so we'll have the value of phi s to be minus 0.24 volt and negative because the bands are bending upwards. Okay, let us then go to the question number 4, also based on the same data. What is the applied gate voltage Vg? So now the gate voltage is asked. So in the diagram we can see that the metal Fermi level moves up relative to the semiconductor Fermi level. So before contact, the Fermi levels were in the thermal equilibrium were this, and now after applying the Vg, the Fermi level in the metal side has moved upwards relative to the semiconductor Fermi level, and this happens when a negative bias is applied. And since the difference in the Fermi levels is given as 0.96, the applied Vg is minus 0.96 then. So the applied gate voltage is negative as the Fermi level moves upwards, and the value is 0.96. So the applied gate voltage is minus 0.96 volt here. Again, let's move to question number 5, a very short question. What is the voltage across the oxide? That is Vox is asked. So we have seen in the summary slide that the total applied voltage gets divided in the so the total applied gate voltage gets divided partly in the semiconductor side and partly in the oxide region. So the total gate voltage can be given as the potential drop on the oxide side plus the potential drop on the silicon semiconductor. So if you just look at the diagram, in our example here, we can say that the phi s value that we have determined was minus 0.24. So if we just substitute in this equation, that is Vg is Vox plus Vs. So Vox is Vg minus Vs, and Vg was minus 0.96 minus Vs was minus 0.24 that we determined. So if we just determine it, minus 0.96 plus 0.24 will give us the oxide voltage drop as minus 0.72 volt. Okay, any doubt here? If not, I'll go to the next question. Okay, so the next question is as follows. So here we have asked to find out the doping density Nd in centimeter per cube, in per centimeter cube rather. So for that we can use the phi f formula. So we know that the phi f, which is the difference between the intrinsic energy level and the Fermi level in the semiconductor side, is given by kT over Q ln of the doping concentration Nd over the intrinsic concentration Ni. Okay, so we need to find out Nd. The phi f value we have determined, which is 0.437. So if you just substitute it here, 0.437, and for the 300 Kelvin temperature, we can write the Vt value as 0.0259 times ln of Nd over Ni. Ni value is given by, I think, yeah, Ni is given by 10 to the power 10 per centimeter cube. So we can substitute that also here. It is nothing but 10 to the power 10. So if you just simplify it, we'll get the value here as Nd would be 0.437.
2.1%
uh,
times 10% something.
I'm sorry.
2.126 times 10% something.
Okay, so I'll just write it down simplified here, that 0.437 divided by 0.0259, and we are taking the exponential on both sides to cancel out the ln here. So we need to do exponential of this particular value times 10 to the power 10. We'll get the value of Nd as Bhuvan has shared. It is 2 times 10 to the power 17 per centimeter cube.
2.126.
Yeah, so in the options you can see all these are approximated, so we can just use the approximated answer here, and we'll get the correct answer as 2 times 10 to the power 17 per centimeter cube. Is it clear? If yes, then I'll need to go ahead. Okay, so going to question number 7 then. Again, based on the same data and very simple questions, just substitution and mere intuition. The 7th question is as follows. What is the width of the depletion region? That is, W is asked. So if you just recall the equation number 6 in our summary slide, you can see that the depletion width is given by this particular relation, which is as a function of the doping concentration and the semiconductor potential phi s. So we can just substitute this particular equation here now. So the W is given by 2 times epsilon naught of sig divided by Q times the doping times the phi s. It is in the square root, that is the raised to is half. So we can again just substitute it here. So 2 times 8.85 times 10 to the power minus 14. Again, mind the units, we are using the CGS units here, times 11.8, which is the epsilon for silicon given. Permittivity Q is again 1.6 times 10 to the power minus 19 coulomb times the ND we determined in the last problem, that is 2 times 10 to the power 17, and the value of phi s was 0.24. So if we just calculate this thing here with respect to the square root, we'll get the value of width of the depletion region W as nothing but 3.95 times 10 to the power minus 6 centimeter, which is nothing but in the nanometer units it will be simply 39.5 nanometers. Okay, so the answer is this. Okay, any doubt here? If not, then let us move further. Okay, so now we are into the 8th question, second last question for this particular data. The question is, what is the maximum electric field on the semiconductor side of silicon and silicon oxide interface? Again, going to the summary slide, we can recall by equation 9 that the maximum electric field in the interface is given by the following relation, that is 2 times Q and D over epsilon s epsilon naught phi s to the power half. Again, mere substitutions as we have been doing in this session. So 2 times 1.6 times 10 to the power minus 19 times the doping concentration, 2 times 10 to the power 17 divided by 8.85 times 10 to the power minus 14 times 11.8. Okay, point the phi s value 0.24. So again, doing this will give us the value, and it would be a negative value because the sign of the E field tells us volt per centimeter. Okay, so the sign of the electric field is indicating the direction of the electric field with respect to the positive x-axis, and in our case on the n side it is negative, so we can get this particular answer. Going to the 9th problem, what is the maximum electric field on oxide side of the silicon oxide interface? Now we are on the oxide side, that is epsilon ox is asked. So for this we can use simply a relation based on the Gauss law, that just a moment, that the permittivity on the oxide side plus the electric field on the oxide side is equal to the permittivity on the silicon side times the electric field on the silicon side. So we need to find the epsilon E ox, that is E ox is asked. So E ox is nothing but epsilon of silicon, that is permittivity of silicon, times divided by the permittivity of the oxide region times the silicon side electric field, that was minus 1.2 times 10 to the power 5 volt per centimeter. And if we substitute the values of epsilon for silicon, that is 11.8, and epsilon for the oxide, that was 3.9 times this, so we'll get the value of electric field on the oxide side E ox as minus 3.66 times 10 to the power 5 volt per centimeter. Okay, so the last problem based on the data is the following. What is the thickness of the oxide, that is our silicon oxide, that is the thickness Tox is asked. Okay, so for that I think we can use simple electrostatic equation that the electric field is nothing but the potential difference, potential drop per unit distance. Okay, so in our case we are considering the oxide region, so Eox is the potential drop, that is Vox, that is in the oxide region, and we are considering, and D is nothing but the thickness of the oxide layer, that is Tox. Okay, so we can just solve for Tox. Therefore Tox is nothing but Vox divided by Eox. Okay, so we have determined the values of Vox and Eox in the previous problems, somewhere I think in the problem 7th or 6th. Yeah, Vox is minus 0.72, Eox also we determined. Just substituting that here, we'll get minus 0.72 of the Vox and minus 3.66 times 10 to the power 5 that we determined in the last problem itself. We'll get the thickness of the oxide layer as 1.96 times 10 to the power minus 6 centimeter. Again, the options given are in the micron and nanometers. So if you just simplify them in the nanometer, it will be simply 19.6 nanometer. So we are seeing the thickness in the 19.6 nanometer here for our case. So it is 19.6 nanometer, this one. Okay, do you have any doubt in these problems which are based on one data? And we'll then move to the final two problems.
Question 7, whites are negative because of oxide.
Which
Question 7,
question?
electric field.
Okay, on the electric field. Okay, so the negative sign is because the electric field is with
Question
respect. Yeah,
7.
7 here.
I think next question.
Okay. Okay, so the answer for this is we have to consider intuitively that the negative sign comes in the electric field, which is because of the fact that the direction of the electric field with respect to the positive x direction we are considering, and it is in the downside on the positive x side. On our case, if you look at the diagram here, here, so with respect to the positive x, the electric field would be downwards, and hence that particular quantity is negative. The amount, I mean the magnitude we have calculated, but the direction we have to intuitively determine, because we are considering electric field with respect to the positive x, and that will give us the negative value.
Right, sir.
Okay, so I think there are finally just a couple of more questions. Okay, so the question number 11 is we are considering. So for this, one thing we can recall is that as we have been emphasizing like for quite few times, that band diagrams are very and like very useful tool to understand what is happening in the semiconductor device. And also, you know, in the last few lectures of the course, we also have been introduced to the concept of block diagrams, also called as the block charge diagrams. So for example, how does the charge vary as a function of position in the Mos capacitor, and how does the electric field vary, and how this potential varies. So all these parameters are quite diagrammatically expressed in the block charge diagrams. So these are very useful and intuitive ways of understanding the MOS capacitors electrostatics. So together with the band diagrams, they convey a lot of information. So we can consider the band diagram, and if you can just quickly recap, if you look at the semiconductor band diagram here, what we can conclude is that what can we infer from these diagrams is as follows. For example, let's say we can look at the bulk Fermi level and then decide what is the doping at the Fermi level. It is closer to EV, that means it is a p-type substrate. Also, if we look to the Fermi level relative to the Fermi level closer to the surface, then we can decide whether the MOS capacitor is in the accumulation mode, depletion mode, or in the inversion mode also. So for instance, in this particular example, we can see that the Fermi level in this case is getting closer to the intrinsic level. That means we are in the depletion region here. So this is quite an important thing to remember, that band diagrams and block charge diagrams are very useful tools. So the question we have asked is in the next slide, but the data given is in the statement is as follows: match the energy band diagrams with the corresponding charge block diagrams shown in the figure, considering the ideal MOS structure. Also, we are asked to state the biasing condition in each of the case. So what we have to do is we have to match the band diagrams with the block charge diagrams, and also we need to state the biasing condition in each of the diagram. So if we just consider the figure number 1, that is band diagram 1 here, you can see that the Fermi level is in the lower side, that is closer to EV. That means it is the p-type substrate, which is nothing but the NMOS capacitor. And as you can see, as we have applied the voltage here, the positive voltage, the EF is moving closer to the intrinsic level, so which is nothing but the depletion of the majority charge carriers, and this is the depletion. And this particular diagram corresponds to the following block diagram, in which the depletion charge minus Q has been shown here. So this is first of all the depletion, and this corresponds to band diagram number 1. We can see the positive applied voltage and the depletion of the negative charges here. If you go to the figure number 2, the band diagram number 2 here, you can see that the Fermi level has crossed the intrinsic level, and the p-type semiconductor in this region has become n-type semiconductor, and which is the characteristics of the inversion regime. For the inversion, as somebody told, that the inverting charge is, as you can see here, that is the electronic charge, and the charge that is pushed away is also shown here. So this particular figure corresponds to the band diagram shown in the figure 2, and this is indeed the accumulation region. As you can see, the Fermi level has been moved closer to the valence level, so this is indeed the accumulation, and accumulation of the positive charge when we applied the negative bias. This is the negative bias, and hence we get the positive majority carriers accumulated at the semiconductor and oxide interface. So this is the accumulated charge, and this corresponds to band diagram number 3. Okay, thanks. Is there any doubt in this? If not, let me go to the final question for today. So the answer is depletion, inversion, and accumulation, and this is indeed the correct option. Okay, so the last question we are about to solve now And this is also a very simple question, but intuitive one. The question is as follows: identify the surface potential ranges corresponding to accumulation, depletion, and inversion in the ideal Tmos device. Okay, so the device given is the Tmos device. That means the inverting charge is P, that is holes, and that means the charge that was inverted from was the electrons. So our substrate is N type. So Tmos is nothing but N type substrate. That one information we can get straight away, and we need to find out determine the surface potential ranges corresponding to these three different regions. So in the N type substrate, let's say if you apply the positive voltage, let's say this is the region. First let's talk about this. So when we applied the positive voltage, the majority charge carriers, that is electrons in the N type substrate, get accumulated because we have applied the positive. So Vg, if you apply positive, then the majority carriers, that is electrons, majority carriers gets accumulated towards the semiconductor and the oxide interface, gets accumulated in the oxide semiconductor interface. So that is one thing. If we applied, say, the negative gate voltage, if we applied negative Vg, in that case the so in that case our majority carriers are pushed. So majority carriers are electrons, and they are pushed away from the interface of silicon and this oxide, and that creates a depletion of the majority carriers, leaving us the exposed ions. So in the 0 to 2 pi phi f case, we get the depletion region, and that happens till a threshold voltage called as twice phi f. And once we cross this particular threshold, the region itself becomes inverting, as the more holes have been surrounding the more holes, the minority carriers have been surrounding the interface, and N type device uh, becomes the P type at the interface. So that means the inversion region starts after this particular threshold voltage, and we can see that the potential ranges corresponding to these three can be clearly explained by option number A here. Okay, so I think this marks the end of today's session. This was the questions that I had selected to uh, answer today. So thank you guys, thank you so much for joining for this session. And
Sir,
yeah,
hello, sir.
tell me.
While applying at the interface, any voltage, negative or positive, is there some limit, the band bending, or it will bend?
Yeah, it bends,
Constant.
as you can see if I go to the figure.
The more it will bend,
Yeah, more
there is.
if it more it bends, it from depletion regime it goes to inversion regime beyond beyond 2 phi f, and you can still invert it, then the concentration of the inverted charge will go on increasing. So that is the case.
Will there be any breakdown, or it will just go infinitely just bend?
Breakdown, I think breakdown, I'll have to see what is the exact limit that we need to. So I think that will also be uh, corresponding to different semiconductors and also the oxide thickness. So this will be dependent on these physical parameters, but I think there will be some limit, but I'll have to check and then I'll get back to you.
Okay, sir. Just intuitively asking, sir.
Okay,
No.
no problem. I think this is a good question, but intuitively I also think that it it must be dependent on definitely the different parameters such as the thickness of the oxide layer, also the which type of semiconductor we are considering, and so on. Okay, so this brings me to the final slide of mine. Thank you guys for joining this session, week number 7th, and I hope to see you in the next live session that is scheduled for the 15th September at 6 p.m. That will be for the week 8, and meanwhile you can go on to the discussion forum of the NPTEL site and open your questions there and discuss different aspects of the assignments and also the lecture content. You can go on my YouTube channel also, where I'll upload the recordings of these live sessions in case you could not join due to any reason or you want to recheck some things. So thanks again, and I hope to see you in the next session. Have a nice weekend. Bye bye.